How do modern smartphones, premium TVs, and advanced displays actually work? Welcome to today's Explainer, where we're going to act like engineers and completely decode the physics behind the screens you literally stare at every single day. If you've ever looked at your phone and thought, wow, how are those colors so incredibly vibrant? Well, you are definitely in the right place. I mean, we see these acronyms absolutely everywhere, right? LCD, LED, OLED, AMOLED, QLED, they're slapped on every TV box and phone spec sheet out there. But today, we're going to cut right through the marketing jargon. We're going to map out exactly how these technologies manipulate light on a microscopic level. Here is our syllabus for the lecture. We're following a sort of evolution of a mission today. We'll start with the foundational physics of OLEDs, see how we upgrade that architecture to AMOLEDs, pivot over to QLEDs for massive brightness, and then we'll wrap it all up with an exam masterclass to really lock in your understanding. Okay, let's kick off our notes with OLEDs. Now, before OLED came along, screens required this big, bulky backlight continuously shining through a liquid crystal layer. OLED was the massive breakthrough technology that completely eliminated the need for those backlights in your premium devices. And that's exactly what allowed them to become so incredibly thin. Let's actually map this out on the board. Looking at this cross-section we're drawing here, notice that organic emissive layer perfectly sandwiched right between the electron transport layer and the hole transport layer. And the whole thing is capped by an anode and a cathode. This incredibly thin, highly engineered stack is literally where the magic happens. So what's the actual definition? An OLED, an organic light-emitting diode, is a self-emissive display device where organic, carbon-based materials emit light when an electric current passes through them. Make sure you write that term down, organic. It doesn't mean it's grown in a garden, it just means the emissive materials are carbon-based compounds. But the absolute key takeaway here is that word self-emissive. The mechanism driving this? It's just pure physics. Step 1, we apply a voltage. Step 2, electrons and holes are injected, and they start migrating towards the center. Step 3, they meet right in the middle in that organic emissive layer and undergo a process we call recombination. And finally, step 4, that recombination releases energy. Boom, a visible photon of light is generated. Now, definitely draw a box around this on your paper. The crucial exam point for OLED is that each pixel is entirely self-emissive. Think about what that means. If an image requires the color black, the pixel simply turns off. It draws zero power, it emits zero light, and it gives you absolute true black levels with an infinite contrast ratio. It's a real game changer. All right, to quickly summarize what we've jotted down so far, OLEDs give us amazingly thin, flexible displays. You get incredible contrast, super fast response times. But there's a catch. They are limited by organic degradation over time. They're sensitive to moisture, and honestly, if you leave static images up for way too long, you run the risk of screen burn-in. But here's the million-dollar question. How on earth do we engineer the control of millions of those individual OLED pixels instantly? Because when you're strapped into a VR headset or scrolling incredibly fast on a new foldable phone, that basic OLED architecture, it just isn't fast or efficient enough to keep up. Well, we solve it by giving the architecture a major upgrade. Notice the addition on the board here. We've introduced a thin film transistor, or TFT layer, directly alongside the organic substrate. Adding this active matrix layer was a massive leap forward in display engineering. And that brings us right to our next big definition on the board. AMOLED. The AM stands for active matrix. Simply put, this means every single microscopic pixel on your display now has its very own dedicated transistor and capacitor acting as an active matrix to control it. Now, the working mechanism here builds straight on top of the OLED chemistry we just covered, but in this case, the TFT matrix acts like a highly trained traffic cop. It rapidly and independently fires specific voltages to highly specific pixels. This is what allows them to refresh incredibly fast, giving you perfectly smooth motion. Get your highlighters out for this exam focus. That active matrix TFT provides independent pixel control. And the so what here is huge. This doesn't just improve refresh rates. It drastically improves battery efficiency because your phone is only sending precise power exactly where it's needed for exactly as long as it's needed. So if we put them side by side on the board, basic OLED relies on a passive matrix. It's simpler, it's cheaper. But AMOLED's active matrix, that delivers superior, high-resolution, high-refresh rate performance. And that right there is exactly why AMOLED is the absolute gold standard for modern premium smartphones today. All right, let's shift gears entirely and talk about the tech that's dominating large-scale, ultra-bright environments. Think massive living room TVs, high-end gaming monitors, or those blindingly bright outdoor digital signs. For those, we need QLED. This is a massive architectural shift. As we draw this out, notice what we're doing. We are actually bringing the backlight back. But instead of just shining it through standard, boring color filters, we're feeding it through a highly advanced layer called a quantum dot enhancement film. Which brings us to QLED, or quantum light emitting diode. This utilizes nanoscale semiconductor particles, the quantum dots, to aggressively enhance color and brightness in an LED backlit LCD panel. And remember, these dots are unfathomably small. We're talking 2 to 10 nanometers. And their exact physical size directly dictates the specific color of light they emit. It's wild. Let's walk through it step by step. First, you've got this incredibly bright LED backlight shining through the quantum dot layer. These dots absorb that light and instantly re-emit it at highly specific, perfectly tuned wavelengths. This creates exceptionally pure, vibrant red, green, and blue colors. And finally, the LCD panel acts like a set of tiny window shutters to actually form the image you see. Okay, put a huge star next to this exam focus point. This is where people get tripped up. Unlike OLED, QLED is literally not self-emissive. It fundamentally requires that LED backlight to function at all. The quantum dots aren't generating their own light from electricity. They are only converting the light pumping in from the backlight behind them. Let's pull up a comparison table, because this is critical for understanding the market. OLED gives you perfect contrast, true blacks, but you carry a little burn-in risk. QLED, it gives you massive, room-filling brightness and zero burn-in because it uses stable, inorganic materials. But it can't quite hit those absolute perfect blacks of an OLED because that backlight is technically always on. Section complete. Now, let's transition from pure theory into our exam-focused masterclass. We're going to take all this knowledge and apply it to a frequent worksheet question I see tripping students up all the time. Here's a classic worksheet question. Compare OLED, AMOLED, and QLED displays. If you get asked to compare these three on an exam, you can't just write down, well, one looks better than the other. You have to structure your answer around their distinct light generation and control methodologies. Prove you understand the underlying physics we just mapped out. Because the examiner is literally just scanning your paper for these exact keywords to grant you full marks. For OLED, you have to write self-emissive recombination. For AMOLED, you must define the TFT active matrix. And for QLED, you absolutely must state that it uses an LED backlight with quantum dots and is not self-emissive. Hit those points, and you're golden. Okay, let's wrap this up with a final revision mind map. Take a mental snapshot of the board right now. If you can master these structural differences, from organic layers to thin film transistors to quantum confinement, and understand how that architecture drives performance, you'll absolutely ace any question on advanced displays. Which leaves us with one final provocative thought. As quantum dots get smaller and even more efficient, are we eventually going to see a hybrid display that is both fully self-emissive and utilizes quantum dots? Keep your eyes on the science, everyone, because the future of the screens we use every day is looking incredibly bright.